All right, so let's see if we can actually get done with this and finish up this case for vectors. So this is the third video for the case for vectors. The first video was just an abstract case for vectors. What I said there is we want the mathematical expression of a physical law to be compatible with our notion of spatial isotropy. So spatial isotropy just means that space, no matter where you are, is the same sort of thing. You can't tell anything about where you are by measuring the properties of space, right? If you're pointed in one direction, you can't tell. You can't tell if the direction you're pointed is north by looking at, how large spatial elements are or something like that. However you would do that, I don't have a really good way to do that because we don't have to do that because space is isotropic. Possibly somebody found some really clever way to measure whether or not that's true. I don't know about it. I'd love to know about it. I mean, I've got comments. If you've got a good way to measure spatial isotropy, go ahead, put it in the comments. Tell me how you do it, and tell me what the current value of spatial anisotropy is in the universe, especially in a local region around, say, Houston, Texas. So let's go with that, and let's go on and talk about what we did in the second lecture, which was just to go and analyze this problem in gravitational attraction, this simple problem that you've seen before, probably in Physics 1, and go through and say, what can we learn from that? What can we do? Well, we analyze this in Physics 1. Probably when you analyze it in Physics 1, you use these orange coordinates, right? These orange coordinates are just coordinates that are made to match the direction of the Earth to the Moon. That way, everything that we do here becomes one-dimensional, right? So we have the system 1, which is the orange coordinate system. It's all one-dimensional. We don't have to worry about the y direction at all because we're pretending the moon isn't moving, is going to crash into the Earth, and everybody's going to be happy. So we just want to find that force coming in that way. We can idealize it as a one-dimensional problem. That's perfectly fine. We might not be able to do that. A lot of times we can't do that. A lot of times we want to do things with, say, the moon moving around the Earth. Then we have to use geometry or something like that to figure out the components of the force. At least we have to figure those things out geometrically if we don't have vectors or something very like them. What we'd like to do is get to this spatially isotropic formulation, the spatially invariant formulation, and that's what this prototype here is. I've used these underscores, or these underlines, to say that these particular symbols represent some kind of mathematical object that, when we move it around, is spatially invariant. All right, and so these are the sorts of things that we have to use to record positions and things like that. So this big R is this x comma y, and this little r is this little x comma little y. All right, so these are just the positions. That's the force, gravitational acceleration, masses, and this d with the head on it is a direction, and that just means that this direction does not affect this magnitude at all. All right. So when I multiply this by this number doesn't change. That has a meaning, mathematical meaning, right? That mathematical meaning is that d with a little hat on it is a object like this with a magnitude of 1, and then all of the angular information gets put in here, right? So this square actually turns this into a number, and we'll talk about that in a moment. And this square has to be invariant because this whole thing is invariant. So these displacements have to be invariant. Distance has to be invariant, excuse me. All right, and then we have magnitude and direction. So this is the magnitude, this is the direction. That's what I've just said. So now I want to talk about this as if these objects, they are complex numbers. And I'm just going to remind you what complex numbers are. You can express them a couple of ways. One is you have the sum of a real and imaginary component, right? And the real component is going to be in the x direction, and the imaginary component is going to be the y direction. You do that, and then you have something that acts like a vector is going to act when you start using vectors. The other way we can express it is by saying it's the magnitude times this e to the I theta, right? Now e to the I theta has a magnitude of what? 1. So this is your direction here, and this is your magnitude. So you see your complex number is a lot like a vector. It has a magnitude and a direction, right? That's what you got told in Physics 1 when you took Physics 1. A vector is something with a magnitude and direction. Well, so is a complex number. Pretty simple, huh? All right, so now we want to talk about how to find the magnitude. Finding the magnitude for a complex number is a little bit different. That's because it's the square root of the complex conjugate of that number times that number. That's not actually a very strange thing. If you get into tensor analysis and stuff like that, you'll find out you can choose, when you choose your axes, that in such a way that they aren't rectangular, when they aren't orthogonal, when they aren't perpendicular like these, then you're going to have to do something very similar to this. It's going to be a little bit different, but it's very similar to that if you want to find distances. You're going to have a space and a complementary space in order to do that. And how that would work is that you take the number in the complementary space, which is this complex conjugate here, so f minus I fx, and you multiply that just by the number in the regular space, f plus I fy, and then you do some math, and it turns out that that's just the square of the magnitude is the sum of the squares of the components. So that's simple enough, and you may have thought about that somewhere in the past. You may have seen that. That is something that you've seen. That is something that you're used to. So you can see already that this formulation is giving you things that you're used to seeing with vectors already. Remembering, of course, that you're already, expert vector people, right? Now we want to talk about the direction. The direction is a theta here, but we want to get it to this little d hat guy, right? That theta then is the arctangent of the ratio of the y and the x components, and then you take that theta and put it into that e to the I whatever. That gives you a complex number with a magnitude of 1, and that's your d. So that's how you get that direction. It's not very difficult. We'll work with whatever's most convenient actually. So we'll probably pull that e to the I whatever out a little bit later. I don't recall because I got a little bit interrupted, and it's been a couple of days since I made these slides. So the first thing I want to do is I want to get all of this stuff into these coordinates in System 1. And after I've got them into System 1, I want to actually apply translations and rotations, which I talked about earlier, in order to get System 2. And if I can do that, then I think I've shown that this prototype, right, if I get this prototype working in System 1, and then I just do translations and rotations, everything should be hunky-dory, right? So here I have my r equals 0, and because the position of the sun is right there in the center of my xy coordinate system, and over here my little r is over here right there, right? DME in the x direction, which means that it's just DME plus I times 0, which is just DME. And then we have this d hat guy. How are we going to figure out this d hat guy? Well, we go through all that fun arctangent stuff. The arctangent of 0 over DME is 0, which means theta is 0, which means d is just 1. It's just the number 1. So the direction in this case is 1. We can express directions in such a boring manner with complex numbers. And we put those numbers in together, and we end up with exactly the same thing, right? We start putting these things in here, DME squared in the bottom, this is just 1, and GMM blah blah blah. Everything's in the I hat, there's I hat direction we said is 0, right? So this is 0, and then all this other stuff is right there. Fairly simple. Now I want to go to System 2. We'll need to talk about how we do the transformations, right? Well, transformations are through rotations and translations. A rotation is just like the direction. It's really, in this particular system, the rotation is just another direction. So it's the direction that we're moving. Now this is sort of this is a passive transformation. We're transforming this thing, so we're moving the axes clockwise, which means that the objects are relatively moving relative to the axes are moving counterclockwise, which means this is a positive number. Okay, and translation, again, you know, we're moving these out here, which means that to the object, we're moving everything backwards, right, this way. We're moving the origin down here, which means that these are positive numbers because relative to the origin here, you know, the Earth is moving, you know, in the positive direction in both the X and the Y directions. So that's what we have. We've got those transformations. Now, how do we apply them? Do I have? Okay, so I thought I had a whole bunch of things here. I only have one. So let's just see how I do it. Well, basically here, this first line, what I've done is I just take, if I want to rotate R, I just rotate it. Or if I want to transform it, I just rotate it and then I translate it, right? Just I multiply by this R theta, or R phi in this case, and then add in the change due to moving the origin. And then I throw all these numbers together and I just get this X plus IY, which you probably could have figured out previously. And you know, you do the same thing with the little r, only he's got these thetas in here to worry about, right? And when you do that with him, you end up with a whole bunch of stuff because we have to do the what did we do before? We did trigonometry and stuff like that. We pulled the trigonometry out for these cosine theta and sine theta so we can get everything the same. So we want to get these numbers into this to look the same as they looked for system 2 before. And then D, we get a whole bunch of fun stuff. You know, we just rotate D, e to the I theta times 1 is e to the I theta. That's all we had to do for that. And then again, we pull out the trigonometry. E to the I theta is cosine theta plus I sine theta, and so cosine theta is adjacent over hypotenuse. Bam, bam, right? And now we've got D is a funny looking thing here, and we just plug those in, and bam, we have the exact same thing. So now, without doing the geometry, we've got the same thing just by rotating something from its sort of natural coordinate system, this XY coordinate system, into this coordinate system that might be useful for your computer, which is you take a picture and then the computer has to analyze it. It's probably easy for the computer to go through and analyze things in this direction. You don't have to do the rotation. Another thing would be you do the rotation to the XY coordinate system, do the math, and rotate back. Right? That's actually a very useful thing to do. So those are the ways to do it. So we've got that all taken care of basically. So I think you're pretty ready for all that other stuff. So we've got this general case in 2 dimensions where we need some sort of object like this complex number, and the complex number is what they'd use in 1800. In the future, in like 30 minutes or whatever, you should be ready to go ahead and just do the same thing in 2 dimensions with vectors. That's where we're going. But we have a spatially invariant form in 2 dimensions and so forth and so on. Probably you want to go ahead with vectors and do the same thing that I've done here. And I don't really have time for the question, unfortunately. You can pause and try to answer it. The answer is going to be both vectors and quaternions, and there's history, and 30 seconds is not enough time for all the fun history involved in this Hamilton and Gibbs stuff. Those are very, very strong physicists that you should know. Just take away that the isotropy of space is reflected in this general case, this spatially invariant form, and transformations on these invariant formulae will give you the correct answer. So you can do a problem in an easy coordinate system and send it back and everything's still fine. All right, well, thanks very much, and I'll talk to you later. Bye now.